Alright, so in today's video we're going to be learning about the basics of what's called work. Alright, so here's the deal. This unit is about work and energy, right? One of the tough things about energy is that you really can't have a full understanding of what energy is without understanding what work, but you can't then understand work without understanding energy. So you get into this sort of circular argument, okay? So this video we're going to learn a little bit about sort of what work is, and then as we go further in the chapter we'll learn more about how these two ideas of work and energy play together and how one affects the other, okay? By the end of this video you should understand how or when a force does work on an object, and you should be able to solve problems using this equation, work equals force dot delta x, which is this, all right? And I'll explain what this dot means here in a minute, so no worries, all right? Okay, so some stuff about work. So first of all, the symbol for work is a capital letter W, all right? And when we talk about work, we're talking about a change in an object's energy, all right? Anytime you do work on an object, you change an object's energy in some way. All right, so what that means is that at least one part of this equation is going to change. When you do work on an object, you're either changing the kinetic energy, or the gravitational potential energy, or the elastic potential energy, or the total energy. Okay? And in order for this to occur, you have to have a force doing the work. Okay? We always say that work is done by a force. So anytime we're finding the work, we're going to find either the work done by one specific force, or occasionally the network, which is the work done by all of the forces combined. All right, now, in order for a force to do work on an object, two things have to be true. All right, number one, first and foremost, the object has to be moving. Okay, so if I hold this coffee thing here, okay, right now it's not moving at all, right? And because of that, I am not doing work. Okay, even though I'm exerting force, I am not doing work. Okay, so the physics definition of work is a little bit different than, sort of the daily language version of it. Obviously I'm going to get tired holding this here all day, but according to the physics definition, I'm not doing work. And an easy way to see that is I'm not changing the energy. Okay? All right, the second thing that has to be true is this. The direction of motion cannot be perpendicular to the direction of the force. Okay? So if the motion is this way and the force is this way, no work is being done. All right, and I'll show you that in an example here in a minute. Okay. All right, a couple other things, and here I'm digging a little bit deeper than. Well, no, I guess that's not true. All right, a couple other things. So first of all, work. It's a scalar, so it doesn't have direction, just like energy. But it can be either positive or negative, corresponding to either a gain or a loss of energy. Okay, so we say that the work is positive if the force is working with the object's motion. Okay, and the work is negative if the force is working against the object's motion. Okay, again, you'll see that in an example. Okay, now later on this chapter, we will learn that there are two different types of forces that are what are called conservative forces. Somehow my bullets have gotten a little mixed up here on the screen. That are what are called conservative forces, and basically all conservative forces do is they convert energy either to or from potential energy. Okay, and then there are non-conservative forces. Oops. And non-conservative forces are important because they are capable of changing the total energy of an object. Okay. So anyway, I wouldn't get too bogged down with these two ideas right now. You might scribble them down. You'll see this again, but I think writing it down now will hopefully give you a little time to kind of process it, before we get to that part in the chapter. Okay? So, here we go. All right, so work is done by a force. So how do we calculate the work? All right, well, to calculate the work, you actually have to use what's called a dot product, okay? So it turns out in math that there are two different ways you can multiply vectors, okay? You can multiply vectors using what's called a dot product or using what's called a cross product. All right. Now, both force and displacement are vectors. So when we find work, a lot of times people just say, oh, it's force times distance or force times displacement. So it's force times displacement. All right. So those little arrows I drew there just emphasize the fact that these things are vectors. Okay. And the type of multiplication we're using is what's called a dot product. okay? And at some point in your math career, you'll learn a little bit more about what a dot product is. When we get to torque, we'll be multiplying these same two vectors, but it'll be a cross product, okay? So for you, I'm not going to go into what a dot product is, but here's how you find a dot product. To find a dot product, you multiply the magnitude of the two vectors. So we're going to multiply the force, however big the force is, multiply that by the displacement, however big the displacement is, and then you multiply it by the cosine of the angle between the two things, okay? So very often, this is the equation you'll see for work in textbooks, okay? Now, I gave two other explanations up here, and I think these will make a little more sense once we dive into some more complicated examples. So let me kind of put these on the back burner for a minute, and when I get to example 4, I will talk about that, all right? So, for now, I think what you need to know is this. Let me kind of help you weed through all this garbage. So here's what work is. If you wanted to write down one equation right now, that's what I would write down, okay? And like I say, as we go through our examples, hopefully we'll kind of clarify this a little bit. All right, and here's the list of all the different variables, okay? And these little notes here will be explained a little bit more in the examples we're going to do, okay? So I think I'm going to just dive in, and we're going to start with this equation that I circled here in red as our jumping off point, all right? So let's calculate some work, okay? So in example number 1, suppose we've got the force acting on the object parallel to the displacement. So maybe we've got something like this. Maybe we've got a box on a horizontal surface. It's got a mass of whatever. The mass isn't even going to matter, but whatever, 50 kilograms. And so here's Roy. Whoa. He's got very long arms, okay? All right, and so here's the force of Roy. So let's suppose that Roy pushes this thing with a force of, I don't know, say 30 newtons. And maybe he causes the box to slide through a distance of, I don't know, 4 meters. Okay? So, what we get then is this. So we get, all right, well, the work done by Roy is equal to the force of Roy dot the displacement of the box, right? Okay, so this is really the force of Roy times the displacement of the box times the cosine of the angle. Now, what do we mean when we say the angle? Well, the angle is the angle between the force and the displacement vectors. So here's my force vector. Here's my displacement vector. Those are parallel, right? Those are parallel. And so in this example, anytime the forces are parallel, the theta is 0 degrees. All right? So this becomes then the force of Roy times our displacement times the cosine of 0. What's the cosine of 0? Oh, well, that's just 1. Right? Remember, the cosine of 0 is 1. So now we've just got the force of Roy times the displacement. Ah, well, that's easy enough. So the force of Roy is 30 newtons. Our displacement is 4 meters. All right, and we can multiply this mess out. Well, I say this mess, it's not a mess. It's just 120. And then the units you get are Newton meters. Well, remember, a Newton is a kilogram times a meter per second squared. So that's a Newton times a meter. Oh, and that gives me kilogram meter squared per second squared. That's joules, which reinforces our idea that work is a change in energy. All right, so there's our work. Okay. And so one of the notes that was given to you on the previous slide said that as long as your force and your displacement are parallel in the same direction, then your work is just equal to force times displacement. Okay? So these are sort of the simple problems. Okay? If force is parallel to displacement. Okay? All right, so that's our first example. Okay? Now, example number 2. What if the force is anti-parallel to displacement? So anti-parallel means that the two vectors are parallel, but they point in opposite directions. Okay? So we'll go back to Superman saving the baby, right? So here's the ground. Remember, we had a giant alien, which I'm going to draw like a Pac-Man ghost. We'll give him claws. I like putting claws on my monsters. Okay, so this monster has just thrown a school bus. So the school bus is sliding this way. Here's Superman. Oh, here's his curl. Cape. All right, so let's suppose Superman is pushing this way with a force of negative, I don't know, whatever, 1,000 newtons, and maybe the school bus is going to slide this way, maybe through a displacement of, I don't know, 50 meters or whatever. This is okay. So once again, we can find our work. Okay, so the idea is the school bus is sliding forward. Superman's going to try to stop it. All right, save the baby. Here's our baby. There. That's a pacifier in its mouth, if you're wondering. Okay, so the school bus is sliding to the right. Superman's trying to stop it. So in this case, look at what's going on. Here's our displacement vector, which I forgot to label. Displacement vector points to the right, and Superman's force acts to the left. So in this example, our angle is 180 degrees, right? Because we've got one force going this way, one force going that way. The angle is 180 degrees, right? As opposed to in the last example, when the angle was 0 degrees, right? Okay, so let's find the work. So work is, the work done by Superman is the force of Superman times the displacement, which is force of Superman times displacement times the cosine of theta, which is the force of Superman times the displacement times, what's the cosine of 180 degrees? Oh, cosine of 180 degrees, that's -1. So times -1. So now we just get negative force of Superman times our displacement, right? Which kind of makes sense, right? Because, oh, you know what I just realized? So to be clear here, I probably shouldn't have put this negative sign here, because the negative sign will come up here, there, right? So basically what we're saying is that the force and the displacement act in opposite directions. So to solve this, we'd have our force of Superman is 1,000 newtons. We put a negative sign to indicate that it's in an opposite direction as the displacement, and then multiply it by our displacement of 50 meters. Okay, in other words, basically either your force or your displacement is negative, right? So what does this give us? 50,000 joules, negative 50,000 joules. All right, so there's our work. Okay, so one of the things that I commented on before was this. Oops, one more slide back. Here. So remember, we said that the work is, positive if the force is working with the object, right? That was example number 1. And then in example number 2 with Superman, the work was negative when the force was working against the motion, right? So the bus is sliding this way, Superman pushed that way, they're working against each other, gives us negative work. Whereas in the first example, Roy's force was in the same direction as the motion, so that was positive work. Okay? So those are 2 of our 4 examples. All right? The third example is a little bit weird. All right? Now occasionally, you'll have a force that is perpendicular to the displacement. Okay? So imagine this. Imagine you've got a box just sliding along a frictionless surface. So I don't know, maybe it's going at whatever, 10 meters a second. The number doesn't matter. And let's make this thing be 5 kilograms. All right, so there are 2 forces on this thing. There's the force of gravity, which would be negative 49 newtons, and the normal force, positive 49 newtons, right? Okay. So when you find work, so let's find the work done by the normal force. So the work done by the normal force is equal to the normal force dot the displacement. I guess we need a displacement, right? How far do we want the box to slide? I don't know. Maybe we'll take a look at what happens while the box slides through a distance of, say, 3 meters. Okay? Doesn't matter. All right? So, so this is normal force times the displacement times the cosine of the angle between the 2 vectors. All right? So something that I think that popped up in that last example that I didn't really illustrate here is when you use this equation, there are no signs in this, okay? Because Fn, this here represents the magnitude of the normal force. This means the magnitude of the displacement, and this means the cosine of the angle. I don't know why I said that. So you don't put negatives into this equation. The cosine of theta part will take care of those negative signs for you, okay? All right, so anyway, so in this case, look what happens. Let's see, my displacement, man, I'm struggling. my displacement is to the right, and both my normal force and gravity are up and down, so they're perpendicular, right? So in this example, our theta is 90 degrees. And what's the cosine of 90 degrees? So think back to your trig. Cosine of 90 is 0. Okay? So I'm going to get my normal force. So this equation is going to give me my normal force multiplied by my displacement times the cosine of 90. I'm just going to get 0, aren't I? Because the cosine of 90 is 0. All right? So anytime the force is perpendicular to the displacement, the work done by that force will be 0. Okay? That is why a few slides ago when I said for work to be done, the direction of motion cannot be perpendicular to the direction of the force, right? Because if the direction of motion is perpendicular to the force, then no work is being done. Okay? So that is huge, all right? When we get to conservation of energy problems, that idea is going to be really, really, really big. So please remember that anytime a force is perpendicular to the motion, no work is being done. Okay? All right, so finally, what happens if the force is at a weird angle to the displacement? All right, so I always do the lawnmower example, right? So if you picture a lawnmower, so here's the wheels of the mower and the motor, and here's the handle, right? Okay, so so if Roy is here pushing this thing, so here's Roy. All right, so the idea is Roy's force is going to be at some weird angle, right, along the handle, okay? So how does this work? All right, well, let's make up some numbers here. So let me make this drawing a little bit smaller just to kind of get it out of the way. All right, so there's our drawing. Okay, so let's redraw this with a little more detail. So here's the mower. All right, here's the force of Roy. All right, so usually we describe the direction of a vector in terms of the horizontal, right? Which in this example makes sense, right? Because the lawnmower is going to move this way, right? So, all right, so suppose Roy pushes, we'll actually do some words here. Roy pushes with a force of, I don't know, how about 40 newtons at 60 degrees below the horizontal. And let's say the mower moves, I don't know, how about 6 meters horizontally. Okay, so the force of Roy here is 40 newtons. Our displacement is 6 meters. And this angle here is 60 degrees below the horizontal, right? So the work done by Roy is equal to the force of Roy dot the displacement, all right? So basically what's going to happen here, well, I'm getting ahead of myself. All right, so let's just do the equation. So this is the same as the force of Roy, magnitude of the force of Roy, times the displacement times the cosine of the angle between them. So that's 40 newtons times 6 meters, I should just do this, times the cosine of 60 degrees. Okay, so grab your calculator and type this in. Cosine of 60 is a half. And so you end up getting 40 times 6 is 240 times a half is 120 joules. Okay, so that's how much work he did. All right? But I want to take a minute and talk about what function this cosine of theta has. All right? So look, here's the deal. Roy's force. We said it was 40 newtons, right? But it's exerted at an angle of 60 degrees below the horizontal, right? So that force has a horizontal component and a vertical component, right? So which one of those two forces is contributing to our displacement vector of 6 meters? Well, isn't it the horizontal component of this force that's contributing to the horizontal motion? So think about how you would find this using trig. Oh, this horizontal component would just be 40 newtons times the cosine of 60 degrees, right? So that's where that cosine comes from, okay? So what I had said was, if you look back here, I told you that you could calculate work by using this, right? Take F parallel times displacement. That's saying take the component of the force that's parallel to your displacement. So this represents the component of the force that is parallel to the displacement, and then multiply that by the displacement. All right. Similarly, if you prefer, it almost never happens, but you can, well, I guess I shouldn't say this. This does come up sometimes. You can take the magnitude of your force and multiply it by the component of your displacement that's parallel to the force. Okay. That really is something that would come up more in AP, but just know that that's a possibility. All right.